Hello and welcome to the second video in my tricky GCSE maths questions, those grade 9 questions, those curveball questions that they like to throw in every year. This particular one is on density and bounds. These tend to be topics that aren't done brilliantly anyway, especially when we talk about bounds within a calculation. So let's get into it. Here we go. We have a question saying that we're going to try and find the density in grams per centimetre cubed of a block of wood, and the block of wood is in the shape of a cuboid. So the first thing I'm thinking here is density is mass divided by volume, and volume of a cuboid, length times width times height. Okay, and just underneath there, we've got three measures, the length, the width, and the height, and it says all of those are correct to the nearest millimetre. So if we're looking at this, they're all in centimetres at the moment. Correct to the nearest millimetre would suggest they've been rounded to one decimal place. So he's measured the mass as 1,970 grams, correct to the nearest 5. And by considering bounds, so there's our confirmation that this is a bounds question. So this here is this line saying correct to the nearest millimetre, correct to the nearest millimetre, correct to the nearest millimetre, correct to the nearest 5. Those would be my first indications that we're talking about something to do with bounds, and that would says confirmed here now. So we're going to work out the density of the wood and give our answer to a suitable degree of accuracy. So it's not telling us what we need to round to at this point. We've got to work that out at the end, and you must show all your working giving a reason for your final answer. So the first place to start then is this section up here with our volume. Okay, so if we're going to look at the volume, we can't calculate density without first calculating the volume for this question. But we're not talking about actual measurements, we're talking about rounded measurements, and we're going to use them in a calculation. We cannot just plug this into our calculator, 13.2 times 16 times 21.7, and then do the bounds. We've got to work out the bounds for each first, because there's a wide variation between what I would get if I multiplied those three together and then did my bounds, and what would actually be the values if I calculated with the bounds in the first place. It's a much bigger error interval. Okay, so if we're starting with the length here, we've got 13.2. So at the first point where I would round to 13.2 would be 13.15, and that one is the one where we are inclusive of the value. On the other side, we'd have 13.25 centimetres. Okay, at that point, so we're not inclusive of that point. At that point, we'd start rounding to 13.3. So now looking at the width, which may be slightly a bit more trickier, but 15 is where we would have rounded, and 0.95 would be where I'd round up to 16 to the nearest to one decimal place. And because this is a 9, it would have then rounded up this to 16. So that's how we know. And on the other side then, 16.05, I'd start rounding to 16.1. And finally, the height, similar to before, 21.65 and 21.75. Okay. And then if I'm going to look at calculating the volume here, this is a multiplication calculations. This is probably the easier of the calculations to do with bounds, because in order to get the lower bound of the volume, I'm just going to multiply these three together at the end, the smaller values at the end, because the only way to get the smallest value of the volume is to multiply together the three smaller values. So I'm going to multiply all of these together. So it's 13.15 times 15.95 times 21.65. And if I pop that in my calculator, and at this point, I really don't want to be losing any of the accuracy. So I'm going to copy it down here, 4540.925125. That's what would come out in the calculator. That's the lower bound. The upper bound then would be multiplying together the three larger numbers. So 13.25 times 16.05 times 21.75. And that, when we plug that into our calculator, would give us 4625 0.409375. Okay, so I've not lost any accuracy by rounding at this point. So I now need to look at the mass. Now it's also telling me that the mass has been rounded. So if we go over to this side, I'll do this in red so you can see this is separate mass. Okay, 1970 grams. And this has been rounded to the nearest 5. Okay, so I'm going to use M for mass in the middle. Now, this is sometimes a little bit more difficult to see. So sometimes a number line helps with when we round into unusual numbers like nearest 5s. So in the middle, I've got 1970. And that means that if we're talking about nearest 5, what's 5 below? That would have been 1965. 5 above would have been 1975. And we know that the middle of these is the points where I would then have rounded to 1970. So the point here, halfway between 1965 and 1970, would be 196.7.5. That's in the middle between 1970 and 1975. 1975 is halfway between those is 1972.5. 1972.5. The other way to think about this is to think about, well, if I'm rounding to the nearest 5, what's half of that? It's 2.5. So what's 2.5 below? What's 2.5 above? So it's half of what we've rounded to. Okay. So there's my bounds now for mass. And this is probably the trickiest bit. So this is the final section. And this is a lot of work in here. So the density. The lowest density and the highest density is what we want. So the lowest and the highest, or the upper bound. Okay, so we want a density is equal to mass divided by volume. And division is where we have to really think about which order I'm putting my bounds in. Now, in order to get the lowest number of my density, I need my lower bound of my mass divided by the upper bound of the volume. To get the upper bound of the mass, I want my highest mass divided by my lowest volume. If you think about the numbers, if I'm dividing a small number by a bigger number, I'm going to end up with a small answer. If I'm dividing a bigger number by a smaller number, I'm going to end up with quite a big answer. So that's how we know that that's going to give us the correct answer. So now the last step, we're going to put all of this together. So lower bound of mass was 1967.5, and I'm going to divide that by the upper bound of the volume, which was 4625.409 and I've put all that in my calculator, and that would give me an answer of 0.42536, and it keeps going. Grams per centimetre cubed is density. So don't forget my units. Using the other side then, we want the mass upper bound. So 1972.5 divided by the lower bound over here. So 4540.92, and like so it carries on. And that gives me an answer of 0.43438 grams per centimetre cubed. And now the final step here, so the final bit, is then we're going to work out giving our answer rounded to a suitable degree of accuracy. If I have a look at both of these, 425, 434, both of them round to 0.43. 0.43 grams per centimetre cubed. So that's a consistent bit in both of them. Yes, they both round to 0.4, but when I'm talking about most of these have been more than one decimal place to begin with, I'm probably going to go to 2. It's a little bit better than one decimal place. It's a bit more accuracy. I would say it's much more suitable degree of accuracy. And the reason that you would give for this, I haven't got a lot of room to write anymore, but your reasoning behind this would be So here we've got to give a reason for your final answer. So the density of his block would be 0.43 grams per centimetre cubed, because both the lower bound of the density and the upper bound of the density round to 0.43 grams per centimetre cubed. So in that case, we can be quite confident it's a good degree of accuracy in saying that that would be a good for the density. So here's the mark scheme. And we're going to have a look then at what we are getting our marks for. So first one is for the correct bound for mass or length, just any one, as long as you have done that one of them correctly, you've got 1 mark. So good place to start. Second mark is for a correct process to find a bound for the volume. So if you found the lower bound correctly, and that could either be shown by showing that you've done these 3 numbers multiplied together and got, or it could be shown by the answer or the upper bound calculation and answer. Okay, so it does say we can accept volumes truncated or rounding to at least 3 significant figures. Ideally, though, you don't want to lose the accuracy, so I wouldn't do so at this point. The next mark here is for a correct process to find a bound for density. So either we've done the mass lower bound divided by the upper bound, the mass lower bound, sorry, divided by the upper bound of the volume, or we've done the mass upper bound divided by the lower bound. So either one of those is okay to get, except densities truncated again or rounded at least 3 significant figures. So there's your next one. The answer for both correct bounds. So at this point, this is where we have found 0.425 carrying on and 0.434 carrying on. And again, those must be at least 3 significant figures. And at this point, if you're stating units, you should be in the correct one. So up here, it said we can work in any unit. So you might have therefore changed these ones to millimeters, for example. But at this point, we're talking about grams per centimeter cubed. We need to be in grams per centimeter cubed, ideally. And final mark is dependent now, this meaning here dependent on you getting an answer correct. So if you haven't got the answer mark here, you cannot go on to get this mark regardless. And it says for a correct statement on degree of accuracy, upper bound and lower bound both round to 0.43 to 2 decimal places or 2 significant figures. Okay, so this is saying it must be 0.43, not 0.4. So it's very clear here that we needed 2 decimal places. So more accuracy for 2 decimal places. And that is how to achieve that. An awful lot of work there for those 5 marks, with 5 marks that you would definitely need if you're going to get that grade 9. Hope that really helped. And I shall speak to you again shortly. Feel free to subscribe for more. Thanks, guys.